Hello everyone, this is Zul Hakim, this is Tong Ming, and this is Saharul. And today we'll be presenting to you the state machine diagram. First, we begin with the introduction of state machine diagrams. So, a state machine diagram is a UML diagram that used to depict the various state of an object may be in, and also the transitions between those states. In other modeling language, it is common for this type of diagram to be called a state transition diagram, or even simply as a state diagram. A state machine diagram is also being used to model the object behavior, as the state machine diagram is located under the behavioral diagram of UML diagrams types. The behavior of an entity is not only a direct consequence of its input, but it also depends on its preceding state. The past history of an entity can best be modeled by a finite state machine diagram, or traditionally known as automata. UML state machine diagrams, or sometimes referred to, as I said before, a state diagram, state machine, or state chart, is used to show different states of an entity. State machine diagram can also show an entity how they respond to various events by changing from one state to another. State machine diagram is a UML diagram that used to model the dynamic nature of a system. So, why state machine diagrams? State machine diagrams typically are used to describe state-dependent behavior for an object. An object responds differently to the same event depending on what state it is in. State machine diagrams are usually applied to objects but can also be used and applied to any elements that has behavior to other entities, such as actors, use cases, subsystems, and systems. And they are typically used in conjunction with interaction diagram or sequence diagram. To make it clear, I'll show you an example. Consider you have $100,000 in a bank account. The behavior of withdrawal function would be balance equal to balance subtract the withdrawal amount, provided that the balance after the withdrawal is not less than 0. This is true regardless of how many times you have withdrawn money from the bank. In such a situation, the withdrawals do not affect the extraction of the attribute values, and hence the gross behavior of the object remains unchanged. However, if the account balance would be negative after a withdrawal, the behavior of the withdrawal function would be quite different. This is because the state of the bank account is changed from positive to negative. In technical jargon, a transition from positive state to negative state is fired or rejected. The extraction of the attribute value is a property of the system rather than a globally applicable rule. For example, if the bank changes the business rule to allow the bank balance to be changed and overdrawn by $2,000, the state of the bank account will be redefined with condition that the balance after a withdrawal must not be less than a $2,000 in deficit.
Okay, so now I will be explaining about the characteristics of state machine notation. So the first one is state. So what is a state? The state is a constraint or a situation in the life cycle of an object in which a constraint holds the object executes an activity or waits for an event. And it is denoted by a round corner rectangle with the name of the state written inside it. So what are the characteristics of state? So state represent the condition of objects at certain points in time. It also can be viewed as moving from state to state. And a state is a point in the life cycle of a model element that satisfies some condition where some particular action is being performed or where some event is waited. Okay, so there are initial and final states. So what are initial state? The initial state is also known as the initial pseudostate, which indicated with a solid circle as in the diagram. So it represents the first real state. As for the final state is indicated with concentric circle. So It is used in open loop state machine where it represents the object before the system terminates. Okay, and then events. So events appear in the internal transition compartment of a state or on a transition between states. As you can see here, in the state created, as the event request shipment is occur, so the state move from created to shipping. So there are 4 types of event. The first one is signal event, which corresponding to the arrival of an asynchronous message or signal. The second one is call event, which is corresponding to the arrival of a procedural call to an operation. The third one is time event, which is a time event occurs after a specified time has elapsed. And the last one is change event. The change event occurs whenever a specified condition is met. Okay, so what are the characteristics of events? So events represent incidents that cause objects to transition from one state to another, just like the example we see before. And then internal or external event triggers some activity that changes the state of the system and of some of its parts. Okay, so transition. The transition is a progression from one state to another and are denoted by lines with arrowheads. So each transition line is labeled with the event that causes the transition. Okay, there's another one, which are self-transition. So self-transition is a state that can have a transition that return to itself, as in the following diagram. So what are the importance of transitions? Okay, so transition is very useful for describing complex behaviors in a system. It also helps us understanding state transitions as a part of system analysis and design. Okay, so I will be explaining how does transition between states occur. So as you can see here, so there is an element in the source state which here passive, and as the event occur, which is transition, maybe we can give it any example. So if the event is occur, so the state will move to the active. Okay, so the element enters the target state. Okay, next is trigger. So trigger is the cause of the transition, which could be a signal or an event or a change in some condition or the passage of time, and it represents the incidents that cause the object to transition from one state to another. Okay, so we'll be looking into some of the simple state machine diagram notation example. So the first one is compound states. So a compound state is a machine diagram that includes a sub-machine diagram. So as we can see here in the example, the machine state diagram consists of another machine state diagram, which we call it a sub-machine diagram. Then choice pseudostate. Okay, so it is shown as a diamond with one transition arriving and two or more transition leaving. So as you can see in the diagram, there is one arrow coming from the state selecting message format, and then it branches into 3 states. So it depends on the event happen. So for example, if the event is voice, so it will be creating voice message. So next is junction pseudostate. So junction pseudostates are used to chain together multiple transitions. A single junction can have one or more incoming and one or more outgoing transitions, and guide can apply to each transition, just like in the diagram. So the last one is concurrent regions. So concurrent regions is a state that is divided into regions containing substates that exist and execute concurrently. So based on the example, it shows that within the state applying brakes, the front and rear brakes will be operating simultaneously and independently.
Okay, Okay, so now I will be explaining about an example of the state machine diagram. For our case study, consider a vending machine that can be found almost everywhere around Malaysia, such as in hotels, in shopping complexes, and also in restaurants. So this vending machine is a coffee vending machine that will dispense coffee based on customer selection. The coffee will only be dispensed after the customer had inserted the right amount of coins and also selected their preferred coffee. After the coffee has been dispensed by the coffee vending machine, the vending machine will then refund the change to the customers. So, how do we draw and construct the state machine diagram? Here is the full state machine diagram that we have designed and drawn based on the case study in the previous slide. So we can see that from this state machine diagram, it consists of symbols such as the initial state denoted by the full black circle, 5 states labeled as S1 to S5, and 8 transitions where one transition is self-transition labeled as T2 and the others 7 transitions labeled as T1 to T8. Finally, we have a last final state which is denoted by a circle with a black dot inside. So I will explain further about our state machine diagram. To start off, we draw an initial state denoted by a full black circle and we will label it as power on. So after power on, the coffee vending machine transitions from the initial state to state 1, which is labeled as S1, where the coffee vending machine is now in an idle state, still waiting for customers to approach the machine and also choose their coffee. Next, the coffee machine transitions from S1 to S2. This will only happen after the customer has inserted the coins into the coffee vending machine. So in S2, the coffee vending machine is now in a state waiting for more coins to be inserted. That is why we draw a loop labeled as T2 for the customers to insert the coins again until the right amount of coins have been inserted. After the right amount has been inserted, the coffee vending machine transitions from S2 to S3. So we draw a transition line, label it as right amount entered, and to state 3, which is labeled by S3. And in S3, the coffee vending machine now waits for the selection from the customers, where the customers will choose their preferred coffee and press the button for the coffee vending machine to transition from S3 to S4. So in S4, the coffee vending machine now makes the coffee from the selection that the customers have made just now. And then we'll draw a transition line labeled as T5, stating that the coffee has been dispensed by the coffee vending machine. And the coffee vending machine now moves to state 5 labeled as S5, where the coffee vending machine will refund the change, if there is any, to the customers. From state 2 and state 3, where the coffee vending machine is waiting for more coins to be inserted and also waiting for the selection from the customers. In this process, if the cancel button is pushed, they will also transition from S1 and S3 straight away to S5, where the coffee vending machine will straight away refund the change back to the customers. This is when the cancel button has been pushed. Finally, after refunding the change to the customers, the coffee vending machine now moves from state 5 back into the idle state S1. Finally, we draw a transition line from the idle state S1 to our final state, where we label it as power off. And the final state is denoted by a symbol, a circle with a black dot inside. So this is how we draw our state machine diagram based on the case study given before.
Well, that's all from us. Thank you.